We're going to continue our discussion of additional natural language processing applications, talking today about coreference. So first, what I'm going to do is I'm going to explain what is coreference, the distinction between old-fashioned rule-based coreference with the new fancy stuff that we're doing in neural coreference, what makes coreference hard, and why the innovations that people came up with to deal with coreference in the last few years has led to the neural revolutions that we've seen for natural language processing. And hopefully this might encourage you to use coreference in your own work and to understand the limitations of existing coref systems. So first, what is coreference? The goal of coreference is to identify the noun phrases or entity mentions that refer to the same real-world entity in some passage. So here we have Queen Elizabeth. She's mentioned by name, but when we use the pronoun her, we're still talking about Queen Elizabeth. And her husband is King George VI. When we say husband, we actually mean King George VI in this context. When we say the king, generally, we're not talking about some abstract king. We're talking explicitly about King George VI and his speech impediment. There are other entities who are not mentioned by name, but who are still relevant. So a renowned speech therapist is not mentioned by name, but this isn't George VI, it's not Queen Elizabeth, it's somebody else, and this person might be mentioned by pronoun again. There are many sources of information that help you solve whether two things are co-referent or not. I won't go through all of them. You can probably think of some of the things that make this difficult yourself. Many languages have gender and number associated with pronouns, and when there's ambiguity in what the pronoun refers to, you need to use the properties of the gender-number agreement for a particular language. There are also syntactic constraints that force some things to be coreferent or not. More broadly, there are discourse constraints on what things can be coreferent. I can't mention they if I talked about the antecedent, what that pronoun is referring to, 3 hours ago. You won't remember what I talked about, and I shouldn't expect you to. Sometimes, when you need to resolve a coreference, you need to appeal to world knowledge. So for example, the dragon found the knight, but he flew away. You know that dragons are more likely to fly than the knight, so this is probably referring to the dragon in this case. And some of these pieces of information are easier than others to teach to a computer. So why might you want to use coreference? One application is question answering. Michael Collins and his colleagues have an interesting paper called QED that recently applied this to real-world question answering, but here's a toy example where you can get a sense of this. Here are two different places where you have something saying he was born in Salzburg, or he was born in Rohau, and in order to figure out which of these is actually referring to Mozart, you need to resolve coreference, and only the top one tells you when Mozart was born. One application of mention detection and coreference is in digital humanities, and this is something that I've worked on in the past. For example, let's say that you want to characterize a relationship between two figures from mythology, literature, or religion. You can look at all the places where they're mentioned, either direct mentions or coreference, and build a word cloud of how they interact with each other, and then characterize their relationship, and maybe find similar relationships in different works. Later on, my former student Mohit Iyer, who's now faculty at UMass Amherst, had a similar project, but he looked at the development of relationships over time in novels. So for example, between two characters in Dracula, they fall in love, they get married, the wife gets sick, she dies, but because this is from the novel Dracula, where there are vampires, that's not the end of the story. She then comes back, and then the husband needs to murder the wife. Detecting these mentions was important to be able to cluster these relationships over time. So remember, Mohit, we'll be talking about him later when we talk about some of the deep learning innovations that have helped us do coreference better. Let's now talk about one of the earliest algorithms for solving coreference, Hobbs' algorithm. The basic idea is that you have some pronoun, you want to figure out what it means. You then have a parse tree that encodes all the syntactic information of the sentence, or multiple sentences. You then climb the parse tree until you get to an S, and then for every noun phrase or S, do a breadth first left to right search of the children that are before, i.e. left, of the pronoun. And then for every noun phrase that you find, check whether it could possibly agree with the target in terms of selectional restriction, number, gender, whatever you can think of. And then keep doing that on earlier sentences until you find some matching NP. So let's go through an example of this from the sentence, "The castle in Camelot remained the residence of the king until 536 when he moved it to London." So let's see if we can figure out the referent of it. Now, we as humans know that this refers to the residence of the king, but the algorithm doesn't know that. So what we have to do is we first have to start with it and then move up the tree until we find an S node. So we've gone up to the NP or PP that contains it. So we have to keep going. So now we found an S node, and there are no NPs to the left of our pronoun that we're trying to resolve. So we can't do anything. So we need to keep going up and keep searching. All right, we've now found an NP. It's 536. We can't move a year. So we reject that and keep going up and keep searching. Okay, now we found another S node. Now let's search left to right. Okay, we found a candidate, the castle in Camelot. You can't move big, heavy things like castles, so that's rejected. So then we get to the residence of the king. This is something that we can move. You can move a residence, so this validates the selectional restrictions. Residences don't have gender, so it matches the gender. Residence and it are both singular, so we're all good. We can accept this. You can do something very similar for the pronoun he. You follow almost exactly the same path, but now you're looking for something that's male, and the only thing that matches is the king. So we call that node in P6 the referent. Normally, in this class, when I talk about some rule-based algorithm, it hasn't been used in decades. But for coreference, the story is very different. Rule-based algorithms are still competitive coreference systems. And up until the mid-2010s, they were the best. And Durrett and Klein have a great analysis of why it's so hard to get machine learning to work well for the complete coreference task. And in some cases, you might still want to use a rule-based algorithm. So we'll talk more about that in a second. And only recently have machine learning approaches become competitive with rule-based approaches. One of the problems that held up machine learning approaches is that it was often viewed as a pipeline. You did pre-processing, extracted syntax trees, detected mentions, and then did coreference. This mention detection bit was particularly tricky because you need to know the pronouns, the names, and everything else, and you need to get it exactly right. Many papers only reported results if you use the gold mentions. So for example, what humans found as potential mentions that you then need to do coreference on later. And that's not to say that the researchers did anything wrong, but if you're trying to compare what you would get in the wild on data where you don't have gold mention annotations, the numbers wouldn't be comparable. And in those cases, the rule-based systems tended to beat the machine learning systems, which were more fragile once you had the messy mention detections that came from other upstream machine learning systems. And because you're making many decisions simultaneously, you can often think about the task as a pairwise assignment to clusters. Are Mary and John in the same coreference cluster? Are John and her in the same coreference cluster? The answer to both of those questions would be no. But you need to decide that hopefully Mary and her are in the same coreference cluster, and that Mary and she are in the coreference cluster together. If you want to view this as a bunch of independent classification problems, you can create features that might give the algorithm clues about whether two things should be coreferent or not. But even though the problem might look relatively simple when you're just looking at two mentions, trying to decide whether they're coreferent or not, when you actually try to put them all together, you can run into problems. Clinton could be coreferent with either Mr. Clinton or she, but not both. And likewise, for example, the name Jing, that could refer to either a man or a woman. You can't make it coreferent to both him and she, even though those individual decisions might make sense, but you then have this transitive implication that him and she refer to the same mention. One paper that broke the logjam for neural coreference resolution was this paper out of Luc Sedlmayer's group at the University of Washington. And this was the first model that didn't take a pipeline, often with handcrafted rules, and applied it to coreference. What this model did is it created representations using both word and character embeddings for every word in a sentence. It then applied a bidirectional LSTM to create representations of the word in context. And this is particularly important for coreference because you're not making decisions about words only based on their intrinsic meaning, but how they function within a sentence. Using this bidirectional LSTM was really effective for capturing how the word works in its sentence. And then for any span, something that could be a coreference candidate, there are three components to the representation. First, the boundary representations that mark the beginning and the end of the span. The third component was an attention-based mechanism that learns the headedness of individual spans. In the Postal Service, the is probably not going to be very important, but maybe you want to focus on postal combined with service to figure out what part of this span is important for figuring out what it's going to be coreferent with. And you don't just do this for the Postal Service, you do this with all possible spans in the sentence. But once you have the spans, that isn't enough. You then need to figure out which ones are coreferent with each other. And this is where there can be some algorithmic trickiness. You can have a polynomial explosion if you're not careful. Take a look at the paper for details. So after you've created a mentioned representation for each candidate, you now have candidate spans. You need to select them using beam search so that you don't blow up the complexity of your algorithm. And then you need to decide, is this a mention that we care about, yes or no? Then you need to decide whether two mentions are coreferent or not. And then you need to assign these to clusters. And then you need to assign these to clusters. One thing that we haven't talked about yet in coreference that's pretty important is that you also have the null cluster or the garbage cluster, where you have mentions that you can't line up with anything else. Your algorithm may think, this is probably important somehow, but I can't line it up with anything, or it's something that's only mentioned once. We're just going to put this into its own little bucket and not worry about it anymore. This becomes the null cluster or the singleton mention cluster. So with this architecture, Kenton Lee and company created the first end-to-end coreference system, and we've had innovation since then using SpanBERT and other models that improve on it, but this helped us get through the impasse that for English on Newswire, coreference was not always better with machine learning than with handcrafted rule-based systems. So what made coreference so hard, particularly in contexts where we were looking at novels? This is something that I care a lot about, and if you're interested in digital humanities, you may be interested in this too, since coreference has a very different flavor in, say, literature than in newspapers. And part of the problem is that most of our training data for coreference comes from newspaper data. This is something that we made a big deal of in a 2015 paper where we tried to make the argument for doing evaluation outside of newspaper coreference data. Journalists are paid to inform they're public. They can't assume that everyone knows about every world leader, so the first time that a new entity is introduced in a newspaper article, there's going to be a little description about who that person is, how they fit into the story. There are specific rules for how you talk about someone. Joe Biden in the New York Times will always be referred to as Mr. Biden. They're not going to call him Uncle Joe or Joe from Scranton or things like that. They're going to be very fixed and rigid. They're going to be very strict and rigid based on their style guide about how they refer to individuals. In contrast, if you look at novels or books or plays, there's going to be much wider variation. Or if you look on social media, oftentimes there are playful or derogatory nicknames that get used for entities without mentioning the person that you're talking about. Beyond nicknames, sometimes there are very generic mentions of entities that are used in literature that aren't consistent with the kinds of references that you see in newspapers. So here's an example from a paper by Rossiger, Schulz, and Reite, passage from Miss Sarah Sampson. Here you have an innkeeper who's saying, "Ein Wirt nimmt sein Geld und lässt seine Gäste machen, was ihnen gut dunkt." And so here, ein Wirt refers generically to an innkeeper, but he's not talking about the obligations of abstract innkeepers. He's talking about himself. He's saying, I'll take your money and I'll let you do whatever it is you want. I'll keep my nose out of your business. But he's saying it in this roundabout way so that he's not complicit in whatever shenanigans they're going to get up to. Another issue in fiction especially is that oftentimes there are multiple universes that interact, and this is particularly a problem when you're talking about an author like Italo Calvino. So in this book, If on a Winter's Night a Traveler, the chapters alternate between two different universes with two different rules for how pronouns are used. And so in some cases, when the author says you, he's talking to the reader. In other cases, when the pronoun you is used, it's being used in a normal novel sense, referring to dialogue or whatever else. No existing coreference system is smart enough to know what chapter it's in so that it can apply the appropriate pronoun rules. One problem of the English-centric focus of natural language processing is that word-level annotation of coreference doesn't make sense. Here's a case where someone is looking for balm, for comfort. That's turned into the beautiful German adjective Trostsuchende, someone who's looking for comfort. Then you have a coreferent. Why are they looking for it from me? But it is referring to just Trost in that big long German word. Existing coreference schemes can't handle that. And if your focus is on novels, a very recent work in Dutch showed that rule-based systems are still doing better than machine learning ones, particularly for long documents in the genre of novels. And part of this is because it's hard to fit long context into models. If you have long-distance dependencies to resolve coreference, you're not going to be able to handle it. And part of the problem is that modern machine learning techniques like BERT have a limit on how many simultaneous word pieces it can look at. So if you have long-distance information that you need to resolve your coreference, it might just have been forgotten in your span-BERT model. So I'd like to take a step back a little bit and think about how coreference has shaped the development of natural language processing. Before Mohit went on to his tenure-track job, he did a postdoc with Luc Zettelmoyer's group in Seattle at the University of Washington, where he contributed to the Elmo paper. One of many people. But if you look at the representation in the Elmo paper, it looks a lot like the bidirectional LSTM, also from Luc's group with Kenton Lee as an author, that solved the coreference problem. It's easy to see the through line that you needed these rich contextualized representations of words. The way that you could get that without being subject to the fragility of parse trees or things like that was using a bidirectional LSTM. Those were incorporated into the ideas that went into Elmo for a general purpose natural language representation that was context specific. This was the specific application of something that really needed contextualized representations that then created the Elmo model that could be used more generally and that in turn started the Muppet craze. We've talked about this before, but Jim Henson, Mohit Iyer, and Jacob Devlin all came from the University of Maryland, and we're all very proud of them. And Coreference played a big story in going from Kermit to Bert. So to wrap up, Coreference requires context-dependent representations. It's a very difficult problem. It's so difficult that it has helped encourage natural language processing to go where it needs to go. There are important applications in digital humanities, bioinformatics, and question answering. We talked about digital humanities and question answering already. Bioinformatics, you can imagine that we're trying to understand how, say, proteins interact with each other, or how proteins and viruses interact with each other. We want to scour every paper on PubMed, see how things interact with each other. It's a lot like what Mohit did for understanding how Lucy and Arthur interacted with each other in the novel Dracula. But we're dealing with proteins rather than fictional characters. And if you're interested in these sorts of problems, there are many ways that you can contribute. A straightforward but difficult thing to do is to get better training data from more diverse domains. If you have that, you might be able to make additional advances on the algorithmic side that you can, for example, make sure that we don't have biased coreference resolution, that we make use of our data efficiently, that we can have a human in the loop to correct model mistakes, or that we can do a better job of incorporating world knowledge and longer context into machine learning models. That's all I have to say about coreference. Hopefully you can see how this fits into the bigger picture of natural language processing, particularly in the pipeline for finding entities, linking them to a knowledge base, and using them for downstream tasks. If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.